Good afternoon, everyone. Thank you for joining us for our Engage session this month featuring Lucy. Lucy is slated to launch from Cape Canaveral Space Force Base in 1 month, and we felt that it was a good time to bring Lucy to everyone's attention prior to launch. The Engage series was created in order to engage the NASA and Goddard workforce in specific missions, project technologies. In this virtual environment, we have expanded that to the larger population outside of the workforce. Special thank you to the Maryland Space Business Roundtable for joining us today for this event. A couple of housekeeping items to go through before we get started. First, the chat feature on the right side of your screen has been enabled in order for you to ask questions of our panel members. There will be an interactive live question and answer session at the end, and we will try to get to as many questions as possible. Second, if you require closed captioning, please hover over the CC button at the bottom of the video. If closed captioning does not work at this time, the recording will be made available shortly after the event ends with closed captioning. At this time, I would like to introduce each of our panel members and moderators that will be participating in this event today. First, Liz McCall from the Lucy Project will act as moderator for today's panel discussion. She will then turn it over to Marissa Ashe, the Vice President of Business Development with AI Solutions and Secretary of the MSBR, to act as moderator for the live Q&A portion at the end. Now, I would like to introduce our panel members for today. Kevin Berry, the Lucy Flight Project's Dynamics Lead, Chanel Duncan, the L. Ralph CSO, Keith Knoll, the Lucy Project Scientist, and Juan Rodriguez-Ruiz, the L. Ralph Thermal Lead. I know that these 4 members of the Lucy team will inspire each of you with their discussion, and I don't want to take any more time away from them. Liz, if you will, please take the virtual floor.
Thank you, Bree. Good afternoon, everyone. Today we are so excited to talk to you about Lucy. As Bree mentioned, Lucy is launching in 1 month. It's actually going to be October 16th from Kennedy Space Center in Florida. She introduced me. My name is Liz McCall. I'm the moderator. I've been at Goddard for 16 years, and I've been on flight projects for 15. I am the project support specialist for Lucy, which means that I have the administrative role and I work in the background to help keep things running smoothly. With me today, as Bree mentioned, we have 4 members of the Lucy team. 2 are from Lucy and 2 are from L. Ralph. L. Ralph is the Goddard-built instrument that is going to be flying on Lucy. First up, we have Keith Knoll, the project scientist. Keith, before you begin, can you give us some information about yourself? Like, how did you get into science and what led you to work to NASA?
Hey, Liz. I can't reveal every detail of that because it would be a little too embarrassing. But let's say when I was a kid, was very influenced by the space program, both the human space program and robotic space program, and by writers, science writers like Carl Sagan had a big influence, and science fiction, both written and television, like Star Trek. And then probably the biggest influence on me was my high school physics teacher, who was one of the first teachers that really treated us like adults. He just gave us problem sets, said go solve them and figure it out on your own. And that was really a transformative experience. So that's what really made the decision for me to go pursue that.
Awesome. I guess, can you tell us a little bit more about the Lucy mission in general?
Yeah, so Lucy is a space probe. It's going to launch October 16th, like you said. It's the first mission to the Trojan Asteroids. And, you know, the Trojan Asteroids aren't what you see on the typical diagram of the solar system. When you're looking from the top down, it just shows the planets. But they are orbiting, if you could make a triangle between the sun and Jupiter, and then the 2 points on either side of that are where these Trojans swarms are. So that's called Lagrange points, Lagrange point 4 and Lagrange point 5. And it's a gravitationally stable region that has trapped asteroids. But the thing that's really made this interesting is that over the last 20 years or so, we've realized that planetary systems don't form and stay the same. They go through a chaotic early phase where a lot of things can happen, including rearrangements of the planets. And what happens to the small bodies, the little bits of the interstellar gas and dust that are forming the planets, is that the leftovers get scattered everywhere. And some of those got stuck in the Trojans. And so we're going there to look for clues. And in some ways, we kind of think of them as fossils of this early chaotic phase. That's where the name of the Lucy mission comes from. It's named for the Lucy fossil, which was discovered in 1974 in Ethiopia, an early pre-human fossil. So that's it in a nutshell.
Okay, great. Thank you. Next, we will have Kevin Berry, the flight dynamics lead, which honestly, flight dynamics is probably my favorite part of the mission. It's just so interesting. Kevin, what type of degree or background did you have to get into flight dynamics?
Hey, thanks, Liz. Yeah, so most people in my branch start out as an aerospace engineer in college, whereas my background's a bit different. I dual majored in math and physics, a little more of that, kind of pure research kind of stuff from a college perspective. And then when I started at Goddard, I learned more about orbits kind of on the job and learned as I went. Getting into the branch, most people come in through internships, and I did as well, but it was an internship at JPL before I started at Goddard. So internships are definitely the most common way in.
Okay. And can you give us a little bit more information on flight dynamics in general?
Yeah. So what we do is mission design, trajectory optimization, and navigation. So starting out at Earth, we have to figure out the whole course to get out to the Trojans and back for our Earth gravity assists, and kind of connecting the dots to meet all the objectives of our mission. So that all happens really early on in the planning phase of the mission, designing the mission, as the name mission design suggests. But then once we launch, then we have to navigate our whole course out there. So we have to take all the tracking data from the Deep Space Network and integrate the solution over time to figure out where we are, where we're heading, and what maneuvers we have to do to correct to get back to that trajectory to get us out to the Trojans. So that's pretty much our job in a nutshell.
You mentioned trajectory. What happens to Lucy after it passes the last Trojan? Will it stay in the same orbit, or will it just keep going?
Yeah, so our final orbit it's a 6-year orbit period. So we go around the sun once every 6 years. The furthest distance of that orbit is about 5.7 times the distance from the sun to the Earth, so 5.7 AU, a little bit past Jupiter's distance. And then the shortest side, perihelion, is a little under 1 AU, so it's a little closer to the sun than the Earth is. So we'll continue on through that orbit forever, because space is big and we're not really passing close enough to anything to disrupt us. So every 6 years we'll fly by the L4 or L5 Lagrange points and repeating for the end, through the end of time.
Hey, Liz, can I jump in and add just one thing? Actually, two. So one thing I forgot to say was that Lucy is unique in the number of objects that it's going to. So we're going to fly past 8 different asteroids, 7 of them are Trojans. And so obviously we really depend on the guys that are driving the bus for us to know how to get us there. And, they're doing it in a very economical way, because we have to, be very careful with our fuel. So the navigation is absolutely critical to the success and being able to do that many objects in a single mission. The other thing is that because of what Kevin said, that we're just going around and around the sun, we put a plaque on Lucy in case any of our distant descendants find this. They'll be able to read thoughts from poets laureate. We have Amanda Gorman, Joy Harjo, other people that put down thoughts that we thought would just tell them something about us when they find this, a million years from now.
Very cool. I guess let's talk a little bit more about LRALPH. Juan, He is our thermal lead on LRALPH. Can you give us some information on your background?
Yes, and first off, I'll say, Liz, I'm disappointed that thermal is not your favorite thing on Lucy. You know,
Sorry.
Thermal is the cool place to be. Yes, my name is Juan, and I'm a thermal engineer. I was born and raised in Puerto Rico. I did my bachelor's degree there, and there was no aerospace engineering option for a degree, but mechanical engineering seemed like the thing closest to it that I could find a way into the aerospace field. So I did my degree in mechanical engineering, and similar to how Kevin was saying, I got an internship to work at NASA while still completing my degree, and I stayed, after I graduated, and I've been a thermal engineer ever since, making sure that things don't get too hot or too cold in space so that they can work and accomplish the great science mission goals that we have set for ourselves.
So you were talking about the temperatures in space. How do you prepare the spacecraft to go into space with the temperatures getting very hot and very cold up there?
Well, when we build our spacecraft or instruments, what we do is we have something we call thermal vacuum chambers. So these are big chambers, big cylinders where you put the instrument inside or the spacecraft, you suck the air out, pull a vacuum so that you can simulate space where there's no air. And then the walls of this cylindrical chamber can get really cold or really warm. And to get really cold, we use things like liquid nitrogen or liquid helium. And we have heater panels and all sorts of things that we use for so that we can simulate the environment of space. And I can talk a little bit more about RALPH. I don't know if that was a question. Yeah, so for RALPH, yeah. So we do that, but before we get to the point that we can test it, we need to do all the design, analysis, modeling, and RALPH is, as Liz mentioned earlier, one of the instruments on Lucy. Lucy has a few other instruments like TESS and Lori, and it's arguably probably the most important measurement for the mission because of what it's gonna teach us about the asteroids that we're visiting and the early planetary formation. And thermal is specifically very important for this instrument because we have to get extremely cold for it to work. So RALPH is an optical instrument, so there's a series of mirrors eventually make their way to two detectors. So a detector is, think of it, you throw a picture with your camera and you capture that picture in an image. Because your camera has a detecting surface, and then that get digitized, and you see the image. Well, similarly, we're going to be taking science type pictures in the visible spectrum, IR spectrum, with two different detectors that are very sensitive. And the IR detector, which is called LISA, has a key challenge that has to go to minus 280 degrees Fahrenheit. That's minus 280, so it's extremely cold. And if we're not able to take it that cold, what would happen is that it's like taking a picture, but all you see is noise, is scrambled image. So if we're not taking it that cold and keeping it there for the duration of the mission, we're not going to get the science that people like Keith and those who are going to be doing the studies need to have. And we have to do this without an air conditioning because there's no air. We also can't use a cryo cooler because we don't have those options. So we have to get really creative with advanced insulation technology, advanced thermal strap technologies to kind of get us cold enough, consistently enough for the duration of the mission. And yeah, it was an exciting, probably the most exciting job I've had so far. Working at Goddard, it was very challenging, but we had a great team. We were able to work together with the spacecraft, at Lockheed Martin, make sure we had a good design and we tested it, and we're very excited for the launch coming up in less than a month now. Yes, Keith.
Hey, Liz, can I do a go back? I'm realizing as everybody talks all the things I forgot to say. So as Juan said, we have three science instruments, LRALPH, which is really two instruments in one. So we've got the visible camera and then the infrared spectrograph, imaging spectrometer. And then we have LURI, which is our high resolution camera. So that's going to get us the best detailed images. LTES is a thermal instrument that is going to, you can think of it as basically a digital thermometer. It's going to allow us to measure the temperature of the night side and the day side of the targets. And that tells us something about the surface and how fluffy or dense the surface is. And then we also have two spacecraft systems that we're going to use for science. So we have our terminal tracking cameras, which are used to, at the very closest approach, guide us into the close approach. But they are their cameras, and so we're going to use them to get wider, lower resolution images of the whole objects as we fly by. And that's when we get the best lighting conditions. So that's going to be really important for us. And then the last thing that we do is we use the high gain antenna, and we're tracking the radio waves from that and looking at the Doppler shifts, and that allows us to measure the mass of our targets, which is also a really important discriminator in terms of, you know, where they were made and are they really outer solar system objects that were moved in and so on. So all these different pieces have to work together perfectly and reliably. And, you know, that's where we depend on our whole team to make sure that it all fits together and it works.
Great, thank you, Keith. I guess since we're talking about Ralph, since Chanel's here, she's part of the safety mission assurance team. Chanel, can you give us a little bit of background of how, like, where you went to school and how you got into NASA?
Sure. So I wish I had a
mission assurance. Sorry.
Absolutely. I wish I had a good and fuzzy story like Keith, and this was my childhood dream, but I don't have one of those to share. But I did, I was always interested in hands-on and building things. And I like, when I heard about NASA, I said, that looks like something that I would be interested in doing. So I joined NASA over 15 years ago. As you mentioned, a part of the mission assurance branch. And for those who don't know what CSO stands for, it's pretty long, so that's why we go with CSO. But it's the Chief Safety and Mission Assurance Officer. And most of my career at NASA has been spent in the mission assurance branch. And our goal basically says it all. We're working with the team, even though we're independent from the team. Our goal is to look at ways to reduce risk of exploring space and Earth, and while doing so, meeting 100% mission success. As engineers and scientists, we would like to think everything works on the first time, and we know as much as we would like that to happen, it's not always the case. So as the mission assurance, I like to think of it as we're the watchers. So we're verifying what we said we were going to do to make Lucy successful, and working on the Ralph instrument. I've worked several missions, Mars mission. This is my second planetary mission. But the experience that you get from your other engineers, your thermal engineers, your system engineers, it's a group effort, it's a team effort, and that's what Goddard so importantly focus on. So safety and mission assurance is not just for my directorate, is a whole. It's the project goal, it's the Lucy mission, as well as the Ralph mission, and all the missions all the instruments that's going to fly on the Lucy mission. So I'm excited for this opportunity. I've gained so much experience working on Ralph and ultimately supporting the Lucy launch. So I'm excited for it, to see the work that it does.
Now, you brought up safety. That's been on the forefront of a lot of people's mind recently with the pandemic. Was there any, can you explain what happened and how you guys kept mission success in the forefront of everything during the pandemic?
Certainly. So as we all know, we're dealing with a pandemic. And when this pandemic started, Ralph was in the middle of integration and ultimately testing. And as the world was, we were shut down for approximately 2 months, which we didn't expect. But it was some things that led up to that before we could just walk away, we couldn't just drop our notebooks and head off center and go home for 2 weeks. We had to ensure that the hardware was safe. And then ultimately, once we were able to go back on center, we had to also make certain that we, when we got the hardware and started doing the integration and tests, that we left it in a safe state. But we also, like I said, safety was at the key core forefront, not just for the hardware, but also for our personnel as well. So we had to work in a different dynamics than anything we've ever done before. You know, normally we could have 60 people in a large clean room. We had to go, you know, cut our staff down to make sure that we were adhering to the social distancing, but also ensuring that we tried to maintain schedule, and we were able to meet schedule during the pandemic. I worked with an awesome team of engineers that were willing to go in and support during the pandemic, and making certain that their safety was at the forefront as well. But it was a challenging opportunity with some lessons learned there. I think we found some ways that we could be more efficient as the safety and mission assurance branch. So it's some lessons learned that we'll walk away with and we can pass on to other projects and other missions.
Yeah, and one thing that I wanted to add as a fruit results for that is that when we started this mission, our launch date was October 2021. And it was a very heroic effort done through the pandemic and all that, so that we're still launching October 2021, which in the middle of the pandemic, it seemed like it was like a mission impossible. And for those of all, who know about space missions, it's not uncommon for space missions to, get delayed. So I think the team has done a phenomenal effort, especially, the safety mission assurance team, keeping us on track to meet schedule and our commitments, which is key because for planetary launch windows, you can't just launch anytime you feel like it. You have to launch at the right time to reach the target because it depends on the right planetary alignments and everything like that. So yeah, that was, I think, a huge accomplishment of the whole Lucy team.
Great. I think that concludes our part of the panel. I guess if I can hand it over to Marissa Shea to see if there's any questions from the chat.
Sure, absolutely. Thank you so much, Liz. I appreciate that. And what a great set of panelists we have. We have a lot of very good questions. So without further ado, here's the first one in two parts. What is the maximum possible mission duration for Lucy? And what happens to the spacecraft at the end of the nominal mission?
Yeah, so it's a difficult question what the maximum possible duration is, because it really depends on what we want to do after we've done our last flyby. So if we're able to just hang out in the orbit we're in, we're not going to run out of fuel and we can go forever. So it would really be dependent on hardware because, out in space, it's harsh. Things fail eventually, but that could be decades. Propellant-wise, what'll happen in reality is that when we're coming up on the end of the mission, we'll start, by we, I mean headquarters, we'll start considering extended mission proposals and trying to use whatever propellant we have available to do more science, do more good things with the spacecraft. So there's no solid answer for how long things can go. It'll depend on what we got left at the time. And then, see, the other question was, what happens after the mission? Yeah, so I did see questions in the chat asking about the worries of us crossing Earth and crossing Mars and all that stuff. And we have propagated out that trajectory for 50 years. That's actually a headquarters requirement for planetary protection to analyze a 50-year range for safety. And we do find that there is no significant close approach to Earth, Mars, or Jupiter. The closest we get to Jupiter is actually when we're at Earth, because we're going 60 degrees off of Jupiter out at 5.7 AU. So yeah, Jupiter's not very close at all. But anyways, when we come back by Earth, the distance is like 20-something million kilometers when we fly by, and it doesn't get any closer than that over 50 years.
Well, except, hey, Kevin, let me just throw out that somebody's not muted, I think. But anyways, we actually have three intentional close Earth drive flybys, and we use these Earth flybys to help redirect. And Kevin, you probably are much more knowledgeable about that than I am. But the first one is just a year after launch, and we think that that Lucy might be visible from if you were standing in the right place on the Earth as it comes by. It gets lower than the space station on that flyby. We do another one 2 years after that, and that essentially boosts us out to the Trojans. And then on the way back from the L4, we have another one that helps redirect us so we can encounter our target, Patroclus Menetius, which is this very interesting binary object in the L5. And that's something we definitely don't want to miss, because we think these binaries are really characteristic of what we see in the Kuiper Belt. So, way out there's lots and lots of these binary objects, and we have one in the Trojans. So we think that is an indicator that it's a particularly pristine object. So we really want to get there, but we need these major changes. And I think the limiting thing is we have only we have a limited number of fuses on our pyrolander, right? So we can't have, we might end the mission with the ability to do one more deep space maneuver. And after that, then we can't, it's just, you actually have to target these things to get close to them.
Right. After we're out of
major
attempts with with the main engine,
and I think the limiting
then we have to use the TCM thrusters, which are smaller, so it's less efficient, but we still can do things, make adjustments. The Earth gravity assists we have are all targeted, throughout the trajectory, and we use them to our benefit to get, boosts, gravity assists. After the Patroclus Menetius flyby, we could target another Earth gravity assist to enable some extended mission, heading back to L4 again. If we wanted to fly by Euripides again, or fly by different Trojans, or even pass by a main belt asteroid, or whatever the scientists think of. And a fourth Earth gravity assist would be very powerful for enabling that kind of science. But without a maneuver,
I'm going to throw it out there now. We should go to Hector, but in the L4. But we're not allowed to talk about extended missions until we complete the prime mission.
Right.
Okay, great. Can you guys explain for us what the design process was for designing the Lucy trajectory?
Yeah, so that actually goes back to the beginning, to the first proposal of the Lucy mission. It was the PI, Hal Levison, came up with the original concept, and Brian Sutter at worked with him to figure out that original mission design. Keith probably knows better than me, but I think the first incantation of that was just going to Euripides. Is that right, Keith?
No, but yeah, it was Euripides and Orus, and then we sort of built it from there. So the important thing about this is you can design a trajectory to go past 5 or 6 Trojans, but the ones that we're going by are relatively large Trojans, and so that means we can actually do science, because if they're much smaller than sort of 5 kilometers or even 10 kilometers, it's pretty hard to do a lot. So these are bigger objects, and they also have some interesting characteristics. So Euripides is an unusual spectral type. There's 3 main spectral types that we see in the Trojans: C, P, and D. And you don't need to know what those mean exactly, but they're just slightly different, and it means that they have different materials on their surfaces, at least, and maybe all the way through. We don't know. But Euripides is also a member of the largest collisional family that's in the Trojans. It's the largest surviving object of what was once a larger object that got smashed to pieces, and we can see all those pieces, and we can tell that they all originally were a single object because they have such similar orbits. So that's fascinating. And then Orus is and Euripides is a C type. Orus is about the same size, but it's a D type. So it's a perfect way to do comparative science, because they're in the same orbits around the sun. They are about the same size, but one's been involved in a big collision and one we don't know, but but probably not. And yet they have these different colors. So it's a way to start asking questions about. And then as we added more and more targets, we get to build this very powerful way of asking all kinds of comparative questions. So that's what's really significant about this trajectory, not just the number of targets, but the interesting mix of targets of different kinds and big enough to get really productive science back from flybys, which is what we're doing.
Yeah, so then the design process was taking those original science targets and then analyzing along the trajectory what the other opportunities are and figuring out how much fuel it would take to fly by any of those other additional targets. And then once there was a concept for which other targets we could fly by, it all gets thrown into an optimizer because there's so many constraints, to do all these flybys that you have to have a big kind of end-to-end optimization routine that minimizes all the fuel to enable it to happen. So that's kind of how the process went. It was the general rough design and then the fine-tuning and the optimization.
So I'll just throw out a fun fact that I heard again recently. We fueled our spacecraft here in Florida last week, and we doubled the mass of the spacecraft when we added the fuel. So more than half of the mass of the whole thing is fuel. And yet fuel is still, something that we really desperately need to conserve. So it's a fine balance between just saying, oh, I want to go over there, but it's going to cost you this much fuel, so you have to do this optimization that Kevin is talking about.
Yes.
And actually, Goddard was a real leader in building these optimization tools. So we have some really great stuff going at Goddard.
Great. Well, a lot of the discussion has been around Trojan asteroids. So we do have a question about what are the primary differences between Trojan asteroids and those found in the asteroid belt. Are they going to be more icy or more rocky?
Yeah, well, so the quick answer is we don't know because we've never been there. So we're the first mission to go. But we actually do know a little bit about them. So two of the targets that we're going to, one of them has a small satellite. The other one is binary. That allows us to get the mass by tracking the orbits. And we have a rough idea of the sizes of these things, so we know their densities. And from that long chain of arguing, we know that the densities are significantly lower than the densities of asteroids in the main asteroid belt. So we think that means that they must be icier, be more porous, have more empty space. So they might be more like styrofoam than a solid rock. But that's a big part of what we want to learn. And that's, for example, what Lisa, and Ralph is going to try to ferret out. Do we see organic molecules? Do we see evidence of water, of hydration? And these are in parts of the spectrum that you can't easily do from the Earth. And you certainly can't resolve. It's at the bottom of this big crater. And, so that means it's, a water or ice deposit or whatever it is. That's what we'll be able to do with Lucy.
Thank you. Is there a recently developed technology that helped to enable this mission?
The one thing that is about, we're going to be the farthest mission operating on solar power. We're going to set the record. So we're going to be a little further than Juno, and we're running on solar power. That means we have to have really huge solar arrays. So that the solar arrays are the biggest things about Lucy. We have two of them. They're each over 7 meters in diameter. I'd tell people it's the size of a badminton court. We're down here in Florida, a pickleball court. That's a relatively new technology, the ability to build these really large, very lightweight solar arrays.
Yeah, I would add a second one. So like I mentioned, we were trying to passively get down to minus 280 so that the LISA detector could get those images that we need to do the science. And one of the things that we did that was fairly recently developed was some advanced thermal insulation that 10, 15 years ago, this was like a small business innovative research fund. So NASA was giving money to different small businesses in the science field to develop technologies that could enable future missions. And this is a technology that came out of that. It was tested on a mission about a few years ago, and we felt like it was prime time to bring it to this mission. And it cut the heat loss or heat input, sorry, by an order of magnitude. So it was not just a 10%, 20%, an order of magnitude heat loss increase, so that we could be better insulated from the warmer parts of the instrument, so we could get cold enough.
Okay, the next question is about LRALPH. Can LRALPH be used to observe Earth from very far away in order to help exoplanet spectrographic experience for astronomers?
Do you want to take a shot at that, Juan?
Well, I think the answer is no,
Yeah.
but you're the project scientist, so you would know what's possible.
Okay, I know, because even though Juan has done a fantastic job of allowing it to get cold enough, we be pretty far from the sun for that to happen. And so by the time we're cold enough, the Earth is just too small and too low of a signal for us to detect.
Will the tracking be at X-band only or X-band plus Ka band?
It's X-band only. We spend so much time out at long distances that we are dependent on the DSN, the Deep Space Network, and it's all of our plans are for X-band.
Will Lucy be able to take advantage of ongoing research at SCAN into future concepts like delay-tolerant networking, or will it be dependent only on DSN?
Just DSN. Our transponder can only really work with the DSN.
Okay. Are there collision avoidance maneuvers built into the software to avoid hitting the asteroids?
So there is no autonomous collision avoidance on board our spacecraft. We will be doing monitoring as we do our EGAs. So when we come into Earth, as Keith alluded to, we're flying as low as 300 kilometers for our Earth gravity assist. As we're coming in, we're going to be taking our trajectory and propagating it forward and running that through the CARA team, which is Collision Avoidance Risk Assessment. And they will be looking at any possible risks of hitting Earth orbiting satellites or orbit debris or anything that is being tracked by them or the DoD. And we'll be ready to do any risk mitigation maneuvers that may or may not be necessary day out. But nothing's autonomous on board. When we're out,
well, except for Kevin, we do have our terminal tracking system, and we use that for the flybys themselves. Because we are, 40 light minutes away at the times of the encounters, we can't joystick these close approaches. So that's all autonomous on board. And the aim point for most of these is about 1,000 kilometers away from the asteroids themselves, which are, anywhere from 30 to 100 kilometers in diameter. So we do rely on that. But I think Kevin is talking more about collision avoidance in low Earth orbit as we do the Earth's gravity assist.
Right. Yeah, we do have autonomous pointing and a whole lot of capabilities in there, but nothing for autonomous maneuvers.
Right.
So out at the Trojans, we are flying far enough away where there is no risk of hitting it. So yeah, we're not really concerned about that, and we can be tracking it on the ground and making any assessments that way.
Yeah, and so maybe just to clarify with the public, so it's not gonna be like the asteroid field in Star Wars where you kind of like to have to shoot them down and avoid them. They're not that close to us. I think, about 1,000 kilometers, which is like the distance from New York to Florida, roughly. So it's pretty far away when we're passing by those. So it's fairly safe.
That's a good description. Thank you. For the general populace, you're right. Why was electric propulsion like the Dawn mission not used?
Do you want to take a crack at that one, Kat? I mean, it's just the trajectory, right? You probably could design a system like that, but they tend to need more electrical power. And I think that would probably be the limiting factor, that you wouldn't be able to supply enough power, but I don't know for sure.
And probably more time, because it's a low thrust over a long time, where we have big, 900 meter per second maneuvers to get us all the way out to the distance we're going to. But that decision was made before I came on the project.
But I wouldn't rule it out in the future, right? I think there are mission scenarios you can think of where electric propulsion would actually be a really good way to go, even as far out as the Jupiter system. So, yeah. But these advances go hand in hand. You need better, more efficient power supplies. You need better solar arrays, more lightweight, and I think eventually we're going to get there.
And Kevin, what optimizer did you use for the trajectory?
Oh, so it's called EMTG, which is the Evolutionary Mission Trajectory Generator. It is open source, so you can just search for it and download it. Yeah, so that was our main optimizer.
Does this mission carry some kind of penetrating radar to investigate its subsurface?
We do not. It's a very interesting idea. And, there's just so many good mission ideas out there. I think that's the one frustrating thing about this business is that, you only ever get to do a tiny fraction of all the really cool things you could do. And that is a really cool thing. And I hope somebody does do it. It's been done on Mars, and you've been able to, probe the polar ice caps. I think there is a question of, for an asteroid, it's not clear because we don't really know the structure of the upper surface, how deep you would be able to penetrate, and then whether you would expect to find enough frozen ice is the main thing you would be looking for at a depth that a radar could reach. So, it's a high risk, but potentially high return kind of experiment.
What are some of the biggest technical challenges compared to other Goddard-led discovery and interplanetary missions?
Can you say that question again? I'm sorry,
Sure.
I missed.
That's okay. What are some of the biggest technical challenges compared to other Goddard-led discovery, such as LRO, and interplanetary missions like OSIRIS-REx and Maven?
I think every planetary mission is a challenge. And, we had to design a spacecraft to do, to be able to go out to the Trojans and carry out the kind of mission that we wanted to do. But to me, the big challenge is the team. And, we have just a fantastic team. Goddard has done a tremendous job of pulling together the experts that we need to be able to get us where we were. And I think, Chanel mentioned this, and Juan, that, we did this in the middle of a pandemic on a schedule that was already actually pretty challenging. When we were selected, that was the one thing that they noted, is that your CD is pretty short compared to other missions. So that's even without a pandemic, that we didn't have as much time as is typical. And yet we somehow are here. So thanks to, this amazing team that we have.
Yeah, on the flight dynamic side, the challenges, the biggest challenges are the trajectory optimization is about 100 constraints. So there's a lot going on there to make sure we can fly by all of our targets and meet all of our requirements and constraints. But then also optical navigation. We're using a really accurate science instrument called LORRI to take images of the Trojans when we are 60 days out. And at that distance, we're really far away because we're traveling at between 5 and 8 kilometers per second. So we have to take this faint image of the target, and then figure out exactly where it is and make any corrections to our trajectory we need to get within 75 kilometers-ish of our target aim point. So that whole optical navigation and maneuver design process in close to the Trojans is a challenge as well.
So just to add to that for LRALPH, one of the early things that we found early on is Keith and Kevin spoke about the LISA instrument that's going to take a lot of great pictures. We had a lot of issues early on with testing when we went into vibration testing because we were testing these usually at extreme limits. And then we found that the isolators kept failing. And that was a challenge. So we had to really go through a whole redesign process. And it took a lot of Tiger team members pulling in the RALPH team, the Lucy mission, and other subject matter experts to understand what's going on and why we were experiencing those failures with those isolators. So we were finally able to get through successful testing. And I think we all just took a deep breath to get us to that point when we were actually able to complete a successful vibration test and then ultimately integrate with Lucy and also complete a successful vibe testing.
I'm going to have bad dreams again, Chanel. Thanks for reminding me of that.
Sorry.
And one challenge that I think of, so because how far away we were going from the sun, and we needed to have very, very large solar arrays, which Keith mentioned, so that we could power the mission. But that created a problem because now our sensitive cryogenic instrument, RALPH, the solar array panel was so large that it blocked the view of it radiating heat to space, and it became the largest source of heat for our instrument, which was not expected when we were doing the early studies. And that was a challenge. But one of the things that I liked about that challenge is that had we not had that challenge, we probably could have gone by with pretty standard thermal control stuff. But instead, we were challenged to find like really creative solutions using that advanced insulation, the diffusion bonded thermal strap, and other techniques that just made it really, really cool mission for us. So,
and Juan, that's when we ended up adding the baffle, correct? To the
yes, yeah, the baffle,
the radiators.
Yeah, we had to make the baffles, and we had to do a bunch of big things and a bunch of little things to make it work with enough margin, because that's one of the things where it can really bite you at the end if you're not careful, and then you go on this mission, you're running 10-20 degrees warmer, and you're wondering what's going on. So, but we tested.
I'd say one of the things that's been most noticeable to me is how agile all of our teams have been, because whenever one of these unexpected challenges gets thrown up at us, people just take a deep breath and then they get on with it, and before you know it, there's a solution, and people are working their way towards that. So it's really impressive.
Excellent. How do you determine and verify reliability of the instruments in the spacecraft?
So I'll kind of chime in first. I'm sure some others had some input, but we go through a vigorous reliability assessment. That means we're looking at every part of the circuit from the board level up to the instrument board, to every part, to make certain that we don't have any single point failures. Where we do and we can implement where it's reasonable, we put in redundancy. There's several different failure mode effects analysis that are reliability. So the important thing is to get the reliability team, engaged early on into the project, to start working with the different subsystems. And you kind of really have to walk through that fault tree logic to see, okay, this is the design, where are my single point failures? How can I mitigate those? Where can I add redundancy? Whereas redundancy is not practical, and continuously report that out to the management team and make certain that you're keeping track of that. Every milestone you should be looking at, where are my major risks and where can I reduce those risks? So those are some of the things for RALPH in particular that we're doing. And some of those things don't reveal themselves until you get into a testing environment. So you catch those things later on. You would like to catch it early in the project, but it's not always the case. So we work in depth with the different project leads, our engineer leads, mechanical engineers. You got to think about it as a whole system and not just your one particular part that you're responsible for, because you're interfacing with other different various. And then you don't want to deliver something to the spacecraft, and then that interface is an issue there. So you got to look at the big picture, but you also got to start at the piece part and kind of work your way up.
Here's a good one. Do you anticipate being able to observe particles escaping from the surface of the Trojans, like on Bennu, which yielded a lot of information about the geophysics of the body?
So we have our science team. It's about 21 members, and we're divided up into different working groups. And one of our working groups is the activity working group. And so they are specifically tasked with thinking about questions like that. We don't necessarily expect it, and because these objects are large enough that they have gravity that's significantly larger than Bennu, and also people have looked for dust trails in all sky surveys, and they're not seen for Trojans. That doesn't mean they're not there, but it means if they are, they're kind of weak. So, to first order, I think Bennu is a pretty different kind of an object. And, maybe one of the things to make a point here is, not every asteroid is the same. In fact, just the way that not every planet is the same, they all have pretty unique characters that depend on their unique histories. And so something like Bennu is probably a rubble pile, a reaccreted rubble pile, and we see these large blocks on the surface, very low gravity. The Trojans are probably pretty different. And so the other factor is that we're flying by, so these are relatively short times when we're close to the object. And even though 1,000 kilometers is close for our instruments, it's not that close compared to how close OSIRIS-REx got to Bennu.
How much time is needed from launch to arrival within 1,000 kilometers of the asteroids?
Yeah, so the mission timeline, we launch and then go around the sun once, and a year later we do our first EGA, and then that puts us on a 2-year orbit period. So then 2 years later we do our second EGA, and then from there it's 3 years until we get to the Trojans. So it's 6 years total, but the first 3 years of that are just cycling around the sun and using the Earth to boost our way out. However, before we get to our first Trojan, we have a main belt asteroid flyby. There's an asteroid named Donald Johanson that we're going to fly by at about 1,000 kilometers. So that'll be 2 years before the first Trojan encounter. So the first Trojan encounter is in 2027. The main belt asteroid encounters in 2025.
Excellent. Okay, we have time for one more question. What are some of the biggest concerns with this mission from a safety and mission assurance standpoint?
I would probably say the solar array is not deploying. Just for, as he spoke to that, that's one of our major concerns. Once we get past that, we have several, concerns, but that's the biggest. So we're looking forward to that.
We're all going to be holding our breath for at least an hour and a half after launch till the solar arrays are deployed, because we run on batteries after we separate from, and we can only run for a couple hours on batteries, so we absolutely need them to work.
Great. Well, thank you all very much, and Bree, I believe it's back over to you.
Well, thank you guys. That was both inspiring and informative, and I can't wait to watch Lucy launch with the whole NASA community and the world this coming October. Thank you all for joining us today, and please stay tuned for our upcoming Engage events and also all of our other virtual events that we have going on at Goddard and the NASA community. Thank you.